A very good morning to Prof. Lin and Prof. Chia. I'm Tien, and I'll be presenting on my FYP Photorealistic Stylized Image Quality Assessment Database PSIQAD Building and Modeling. The flow of this presentation is as follows. First, I'll be sharing the background and motivation behind this project, followed by the project objectives and contributions. I'll then move on to talk about the building of PSIQAD and how it can be leveraged through the creation of baseline objective Stylized Image Quality Assessment (SIQA) models. Afterwards, I'll share some of the results of the modeling. Lastly, to conclude and propose some work that can be done in the future. Image quality assessment (IQA) tasks have become increasingly important with the rising use of imaging devices and image editing applications such as Photoshop. IQA can be used to improve consumer satisfaction via automatic monitoring of the qualities of massively distributed pictures and videos and to perceptually benchmark picture processing algorithms such as compression engines, denoising algorithms that substantially affect viewed picture quality. Despite having several existing IQA algorithms, they usually only evaluate the degradation or aesthetic aspect of an image. With the emergence of partially artificial images, PAIs, there will be more challenges to the applicability of conventional IQA methods since both enhancements and distortions exist in the generation process of PAIs. PAIs are images that contain naturally captured visual components and artificially generated components. This is because the design of conventional IQA methods mainly involves the knowledge of human visual system (HVS), which is treated as a system modeled via natural scene statistics theory and is only highly adaptable to represent the statistical properties of natural images. In addition, the main purpose of these conventional IQA methods is to measure the disruptions of the naturalness introduced by distortions, and thus the adaptations of these conventional IQA methods to PAIs would not work, as PAIs consist of artificial components. Images generated from Neural Style Transfer (NST) are a form of PAIs. There are two types of NST: artistic and photorealistic style transfer. In this project, the focus is on photorealistic style transfer. In fact, style transfer, which is a technique to change the style of the original image to that of a reference image, has become one of the hottest topics in deep learning research. Along with the rapid advancement in this area, NST is even brought over to advanced image editing. One example is a GAN-based model in a training strategy to achieve photorealistic style transfer and to enable automatic image editing, which allows end users to transform their images in just a few clicks. And even mobile applications, making NST becoming more relevant in our daily lives. This makes the understanding of visual perception on PAIs, specifically stylized images, important to reduce costs and improve user experience, such as an image editing application only recommending styles that were likely to be appealing or an image search engine only displaying images that are of high quality. One of the main roadblocks of IQA is the lack of an IQA database that contains images with both degradations and enhancement. Existing IQA databases made for technical assessment consist of only natural images with artificial distortion types, and the distorted images are usually afflicted by only a single type of synthetically introduced distortion. Existing IQA databases made for aesthetic assessment consist of either only natural images with semantic and photographic style labels or processed with limited enhancement types. Also, conventional IQA methods focus on either technical or aesthetic quality of an image separately. Distortions such as irregular patches of color and structural loss, which we will observe later, seem to occur sporadically in stylized images despite the several work to improve stylization outcomes, which were only focusing on different implementation methods. After highlighting the research gap, our project aims to first investigate humans' preference for stylized images and whether both the technical and aesthetic quality affect human perceptual quality. Technical quality assessment deals with measuring pixel-level degradations like JPEG compression, while aesthetic assessment captures semantic-level characteristics associated with emotions and beauty in images. Second, to show how a richer IQA database could enable new IQA applications. And last but not least, through PSIQAD, this project aims to open a new research area in NST to improve stylization outcomes by working on the derived features in the original and style images independent of the algorithm. The principal contributions of this project are as follows. Firstly, a novel database PSIQAD was created and used to advance the study of the evaluations of PAIs, specifically stylized images. Secondly, through the study, the difficulties in assessing the quality of PAIs were explored, in which the shortcoming of conventional IQA methods on stylized images was demonstrated. Thirdly, baseline objective full reference and no reference stylized IQA models were created to predict the distributions of human opinion scores on stylized images. And lastly, through PSIQAD, we were able to conclude that humans are unable to distinguish between technical and aesthetic quality. This highlights the need to consider both the technical and aesthetic quality in predicting perceptual quality, especially in the case of PAIs. PSIQAD comprises of 91 original and 1,747 stylized images from 13 different categories. The 1,747 stylized images were obtained after filtering the initial 1,885 images during subjective tests. And unlike the existing IQA databases, stylized images in PSIQAD comprise of both degradations and enhancements. The source images comprised of style and content images were collected from various image websites and well-known databases. The characteristics of the source images obtained were from a set of requirements for benchmarked image dataset, which includes challenging images, photographic images, and range of appeal. PSIQAD is constructed with a mix of three different renowned photorealistic stylization algorithms, in which the three algorithms were chosen based on the recency of the paper, acceptance of the paper in renowned conferences, and a distinction in methods used across the different algorithms to ensure a well representation of stylized images. The algorithm is then used on the source images to generate the stylized images. With a total of 1,885 manually curated stylized images, a double stimulus impairment scale procedure was conducted in the subjective test. 8 subjects from the School of Computer Science and Engineering, aged from 18 to 25 years, were engaged. The subjective test took place in one of the school laboratories, and each evaluator used the same desktops with calibrated LED monitors. 1,885 pairs of images were broken down into 5 sessions of 30 minutes each with 377 pairs of images. Each evaluator was given the same pairs of images, and there was no overlap of images across the different sessions. This is the testing phase interface, where an evaluator was required to rate each stylized image with one of the 7 options ranging from much worse to much better. Before the processing of subjective scores, a preliminary analysis was done in which 2 issues were identified. First was the presence of extreme ratings. In other words, 2 peak distributions where half of the evaluators preferred the stylized image and another half did not prefer the stylized image. The second issue was how some images had significant variations in ratings among the evaluators. A standard deviation of 1.5 was later used as a threshold to identify these images of high variation for further processing. Images with either of the 2 issues were analyzed. 4 hypothesized factors, brightness, saturation, style, and monochrome were identified. For example, the first factor, brightness, suggests that the determining factor between the pair of images is mainly due to a difference in brightness, where, for instance, one evaluator may view a darker image as more appealing compared to another who may think otherwise. One or more of these factors were hypothesized to be present in the images that resulted in either one of the issues, thereby suggesting that the variation comes from the relatively high subjectivity of the image and not because of the unreliability of evaluators. This is a summary of the processing steps done on the subjective ratings. Images with 2 peak distribution were first discarded, followed by converting ratings of the remaining images to their differential mean opinion scores, DMOS. For each stylized image, the rating with the highest difference compared to the mean of DMOS was discarded, and images with more than 1.5 standard deviations after the re-evaluation were discarded as well. Images that were preferred have DMOS of less than or equal to 0. Hence, a total of 1,747 images were accepted and were made out of PSIQAD. There were instances where evaluators rated stylized images as better looking despite having visible distortions, such as images B and C. This implies that the evaluators could be accepting the color degradation as part of the style of the image, or the style imposed on the image is much preferred by the evaluator, such that it makes the distortion insignificant during evaluation. There were also instances where stylized images that do not have visible distortions were rated as worse off, such as images E and F. Since stylization is considered as a type of distortion with possible enhancement, the presence of positive subjective scores also proves the assumption that humans are unable to distinguish between technical and aesthetic quality, which shows the need for prediction of perceptual quality to consider the two aspects, especially in the context of PAIs. The goal of the proposed objective SIQA models is to predict the distributions of human opinion scores on stylized images. The DMOS values obtained were classified into 7 classes using histogram binding. To curb the imbalanced dataset, data augmentation was applied to the minority classes 0, 1, and 2. Stratified sampling was used to split the dataset into an 80% and 20% ratio, where the minority classes were given more emphasis in the training phase. The proposed FR-SIQA model adapted Siamese network for feature extractions of both stylized and reference images, and feature fusion is used to allow the joint regressions of the features extracted. The selection of an appropriate saliency model is crucial for the success of the model, and this may not work in PAIs. Because, to date, the concept of saliency is known to rely on the simplifications of the human visual system, where the natural scene saliency and the image distortions are treated separately. To increase the stability of the network, batch normalization is used, while the dropout strategy with 0.4 dropout probability is also added, which increases the robustness of the model. The proposed NRSIQA model adapted the convolutional layers with 1x1 kernel size and 512 filters to utilize more nonlinearity in the network. Only the global average pooling is used to focus more on overall features instead of only detecting the salient features. Another difference is the use of batch normalization with dropout as a regularizer. Both the full reference and no reference models used categorical cross-entropy as a loss function for training. And the backbone for both models is ResNet50, which performed the best among the few different state-of-the-art classifier models that were explored. The results reported here are based on 10 experiments of 2000 EPOs with random 5:1 train test splits. The FR-SIQA model was able to achieve an average validation accuracy of 68.58% over 10 experiments. As seen from the confusion matrix, there were no misclassifications of extreme cases where most of the incorrect predictions were misclassifications of only up to 2 differences in class. However, classes 3 and 5 seem to have the largest proportions of incorrect predictions. The overall 10 experiments are also shown in the form of box plots. The performance of the proposed model was compared against 8 traditional FRIQA metrics and a CNN-based FRIQA model that inspired the proposed model. The proposed model fares the best in terms of having relatively higher consistency between the predicted scores and the true DMOS. This is expected because while the traditional FRIQA metrics usually only account for a single type of distortion, stylization itself is a type of distortion with some level of enhancement. PSNR is the next best metric despite being a pixel difference measurement, which usually is reported to not correlate well with the human visual system. The CNN-based FRIQA model trains on KADID10K database of artificially distorted natural images performed worse off as well. The red line shows the predictions after fitting a linear regression to the prediction and ground truth, and in most cases, the proposed FR-SIQA model predicted a difference of 0.5 in scores as compared to the ground truth, and this is inferred from the graph and the equations of the line, which has close to unit gradient. The CNN-based FR-IQA model was much worse off compared to the proposed model. Likewise, for the traditional IQA metrics, they fare much worse compared to the proposed FR-SIQA model with a huge difference in the predicted scores and the ground truth, and this is interpreted from the graph and equations as well. The NR-SIQA model achieved an average validation accuracy of 68.66% over 10 experiments. Likewise, there were no misclassification of extreme cases in which most of the incorrect predictions were misclassifications of only up to 2 differences in classes. However, classes 4 and 5 seem to have the largest proportions of incorrect predictions. The proposed NR-SIQA model was compared against 4 traditional NR-IQA metrics and Google's Neural Image Assessment (NIMA), which the NIMA Static Model was trained on AVA database and NIMA Technical Model trained on TID 2013 database. The proposed NR-SIQA model performed the best as compared to the traditional NR-IQA metrics and CNN-based NIMA models. The traditional NR-IQA metrics performed very badly with close to no correlation between predicted and ground truth. Likewise, the proposed NR-SIQA model was able to predict relatively well with only an average of 0.5 difference in predicted scores from -3 to 3. It is also observed that NIMA technical model performed much better than NIMA aesthetic model, which suggests that the technical quality that has been degraded in some stylized images consists of pixel level degradations similar to that of the images in TID 2013. However, the NIMA models were still worse off compared to the proposed model. This suggests that the pre-trained IQA models on AVA or TID 2013 databases were unable to adapt easily to PAIs, as they failed to exploit what was learned regarding synthetic or authentic distortions on natural images. There will be two scenarios in the demonstration of SIQA models. The first scenario comprises of images with either obvious enhancements or distortions. Here, the first two stylized images that we use are observed to have obvious visible color and structural distortions. The other two stylized images are observed to have obvious enhancement in terms of higher contrast, sharpness, and color. The second scenario consists of difficult images. Difficult images are images that have both visible degradations and enhancements. Apart from the individual styles in each stylized image, all the stylized images here are slightly sharper than original image, with the first stylized image having higher brightness, second stylized image having a monochromatic feel, third stylized image having a slight distortion, while fourth stylized image being slightly more saturated. With these different characteristics of images in the two scenarios, we shall see how the models predict them. Overall, we notice that for unconventional images, that is with high subjectivity in nature, such as images with slight degradations and enhancements, the SIQA models predicted same to slightly better or same to slightly worse. This is in fact quite representative of the human quality scores because of the high subjectivity nature, where some evaluators may consider them as better and some may consider them as worse off. Here are some of the qualitative examples of the ranking of predicted scores by FR-SIQA model in the different percentiles of exclusive range, where the higher the predicted score, the less appealing is the stylized image over the original image. We observed that there is strong correlation between the model predictions and the visual quality of the stylized images. For NRSIQA, the model's predictions are also well correlated with the visual quality of an image. However, there was no drastic difference between images that were predicted close to the median range, that is between the 25th to the 75th percentile. Overall, FRSIQA and NRSIQA models still performed reasonably well as they are able to capture the perceptual realism under this task. In conclusion, in this project, a novel database of 1,747 stylized images was created with a subjective test conducted and used as ground truth. As a demonstration of the usefulness of PSIQAD, objective SIQA models were created to predict the distributions of human opinion scores on stylized images. FRSIQA model was able to achieve at least 23% higher in terms of PLCC, SROCC, QROCC than existing IQA methods, and at least 40% higher for NRSIQA model. The advantages of PSIQAD with respect to the existing databases were also reviewed. This project also proves that humans cannot clearly distinguish technical quality from aesthetic quality, and hence perceptual quality should not solely contain degradations in the context of PAIs. There was also a hint of possible relationship between degradations and aesthetics in an image, where there can be instances that humans perceive the existence of degradations further contribute to the aesthetic of an image. However, there are two limitations in the project to be discussed. First is the complexity of the images in PSIQAD. IQA is a difficult problem. Although humans can easily recognize the type of style, the visual style and aesthetics are very difficult to rigorously define by a machine. There is no specific kind of enhancement or distortion in stylized images, unlike a conventional IQA problem with artificial or natural distortion of natural images. Another limitation is the small number of subjects involved in the subjective test. With a small number of subjects involved, there is a wide confidence interval which leads to statistical indistinguishability of many DMOS and task images, making discrimination of the extent of image appeal difficult. There are two main recommendations for future work. First, score prediction is a highly challenging problem mainly due to noise in human ratings. One way to improve the performance of SIQA models would thus be creating subsets of PSIQAD where each subset has images with similar features. This could be done by manually curating easily distinguishable images or having specific feature assessment in subjective tests, similar to the one done in AADB database. With the different features that subjects use to evaluate the quality of stylized images, it is possible to impose perceptual weighting or pooling strategies on the network to account for the different aspects of visual sensitivity. Second, SIQA models could be used as an improvement in NST. Currently, there was an attempt that uses NEMA as a loss function for NST but could not achieve significant improvement, with the hypothesis being no correlation between images looking photorealistic and looking good. However, with SIQA models that are able to handle both degradations and enhancements, they could be better suited for photorealism loss caused by stylization in NST. Before the end of this presentation, let's take a look at some other interesting stylization applications that are slowly emerging. With that, thank you so much for your time to sit through my presentation and to review my FYP.